What's up guys, Technological Ultimate Gaming here. Welcome to a tutorial on Dreams on how to create Hamming codes. Now, if you don't know what Hamming code is, that's fine, this tutorial is actually made for you. Hamming code is a source of error detection that only works if there are odd numbers. So, for example, it can fix an error if there is one mistake, but it can't if there are more than one mistake, and it can only detect 3 or 5 or 7 errors. Normal Hamming code. There is an extended version which requires an extra bit, but I don't really know how to implement that yet. So a Hamming code. So this is a 1511 Hamming code, which basically means that there are 15 bits. As you can see, this is a 15-bit. These are 15 bits, and 11 of these are your message. The 4 bits are the parity bits, and parity bits turn on and off depending on the group that they are, the amount of ones or zeros that in the group that they are in. So let's say that these, I'm going to actually do this. So these these chips, they are the actual message on its own and how it looks like in the binary. So let's say we want 3 to be on, let's say we want 5 on, 6, and let's say 11 to be on. And this is what it looks like, okay? These switches, they are responsible for making a mistake. So let's say that there was somewhere a mistake and an extra bit number, let's say that number 1. Now number 1 is in position. This is 1, 2, 3. The bit is in position number 1. Excuse me, in position number 3. So we turn on number 3, and you can see this bit, this microchip, which is supposed to be a bit, lights up, and we can see the error and where it is displayed. It's displayed in it's number 3 that has an error, and this is number 3, position number 3. 0011 is 3 in binary. And then this is the fixed position. Now I didn't just copy these signals from up there, I actually did the actual logic for this. Okay? And if this may look complicated, don't worry, it's not that complicated. We could actually got in fact some of these guys removed. I think that one is correct. I think we can remove this guy, and this is 4, 5, 6, 7. We could, I think, remove one more, which is this guy, and it wouldn't affect the message. Yeah, but I added there, and we could remove these guys. So the parity bits, they're not right in the message. The message is still intact. It's whatever is in here is exactly the same as in there, even though there are no parity bits, because the computer doesn't read the parity bits. And the parity bits are there just to detect if there was an error. Okay? And these are all of the different possible outcomes, because there's 11 of them, because, well, it can be any one of these switches. I had any one of these 11 bits. I had to do 11 possibilities. And I'm going to explain how I did all of this in just a second. So, first of all, I want to go through what a parity does, and what does an XOR gate do. An XOR gate is an exclusive gate. So let's say that we have I'm actually just going to show it. Where's the microchip? Microchip is right there, and this is unscripted, as you can probably tell. We do this, we get ourselves an XOR gate. XOR gate can do two things, two really useful things that are keys to Hamming codes. Switch and switch. So in Hamming codes, it's like a universal agreement that if there is an even amount of bits, there is no error at all. And how do we detect if there is an even amount of bits on? So let this be bit. So let these two switches be bits. If none of them are on, then of course 0 is an even number. There's no mistake. If one of them is on, then the XOR gate is on. If the other input is on, well, one is is not an even number, so the XOR gate is on. But if there are two of both of them are on, well, we've got 1 plus 1, which is 2. 2 is an even number, so the XOR gate detects no error. And we're gonna use the fact that 1 is an error, 2 is not an error in our Hamming code. Another useful thing is that they are great like NOT gates. They are like an advanced NOT gate. So let's say that this signal was always on, and right now I'm gonna actually grab a NOT gate for demonstration purposes. So right now both of these signals are on. Okay, we can prove this by having two microchips, plug them both in. Okay, and if you click on this, both inputs are inverted. Now what's useful about the XOR gate is that you can also invert the other thing. So as you can see, I invert this, the signal is inverted, but the NOT gate is not inverted. Instead what we will have to do is this. And even then, it would still not be inverted. So we're going to use these two properties. So I'm gonna save that in a separate microchip, just for clarification and stuff. Okay, so this is demonstration purposes. Okay, next what we are going to do is we're going to bring up another microchip, and inside this microchip we're going to put down our parities. So this is even, so therefore the parity doesn't need to be on. But if it's, so it doesn't mean it needs to be on. But if it's uneven, the parity has to be on to make the code even. And if it's not even if the parity is even, then we are certain that there is an error somewhere. And I'm going to explain how in a second. This right here, this would be our table of contents. This is going to be our just simply table for parity bits, and to keep us organized, which parity bits keep track of which bits. So we're gonna just simply put this thing from there right into this chip, and we're gonna do the same thing from there. These, as you can see, these are not connected. They have these chips have only this, but they can also be empty. And the reason why I'm using these chips is because these chips are colored. These chips are colored, so purple is the color for the parity bit, and yellow is for the actual information bit. And this is just to tell you which table is used for what. So this has to be on. So this guy has to be on. There we go. So this is what it looks like. In our code, we're gonna have the first parity bit at the start as position number 1. This will be position number 2, and it's going to be our next parity. Position number 3 is going to be our first actual information. Position number 4 is going to be our next parity. And in general, if 2 to the nth place is going to be a parity bit. So this is the first place, which is 2 to the power of 0, which is the 1. This is the second place, which is 2 to the power of 1. Fourth place, 2 squared, is going to be the third parity. 2 to the power of 4 will be the fourth parity. Yeah, 2 to the power of 0 is the first parity. 2 to the power of 1 is our second. 2 to the power of 2 is going to be our third parity, and 2 to the power of 3 is going to be our fourth parity. So the parity is the number of parities minus 1. So this is the fifth parity, and it's in position 16. It's always going to be a multiple of 2. It's going to be a power of 2, I should have said. Parity will always appear in the power of 2. And each one of them looks for a different pattern. So parity bit number 1 has a pattern of 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. You get the point. Parity bit number 2 has a 1, 1. Starting at digit number 2, we have a 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 1, 1, 1. Starting at position number 4, parity bit number 3 has 4 things on. So parity number 2 is at position 2 and has 2 at a time. Parity bit number 4 is at position 4 and has 4 bits turned on at a time. 1, 2, 3, 4, and the next 4 are off. 1, 2, 3, 4, and then the next 4 are on. 1, 2, 3, 4, the next are off. Including this guy, this parity right over here is also off. And the last guy checks for groups of 8. So the first 8 bits are off. The next 8 bits are on. So 1, 2, 3, 4, 5, 6, 7, 8. The next 8 are off. So 1, 2, and the next 8 are off. And we will use this table to just have a simple version of what we actually need. Yeah, you don't need the top part, but yeah. So now that I have explained what the parity bits kind of do, let's actually get into coding. So we're not gonna use a 1511 Hamming code, because that would be ridiculous. We're gonna use a simple 4-bit for 74 bit. Okay. So we have 1. Where we have 7 bits total, and 4 of them are free to change. So we have number 1, number 2, number 3, and number 4. Now we have to create our first parity. The first parity checks for 1, 3, and 4. Okay, that's what we're gonna do. It's going to check for 1, 3, and 4. We're gonna plug in 1, 3, and 4. So number 1. Excuse me, did I say 3? It has value number 1. So excuse me, bit number 1 is on. It's going to check for bit number 2 and bit number 4, not bit number 3. Bit number 1, bit number 2, and bit number 4. Okay. And if there's an even amount, and if there's an odd amount of what do we call signals, there's an odd amount of signals, the parity is on to make it even. Okay, so that's exactly what we are doing. If we switch, for example, 2, well, we still have number 1 and number 4 on, and the 1 plus 1 is 2, and 2 is even, so therefore the parity bit is off. We do the same thing for the rest, so we copy this, paste it here, right there. And now, this is going to be our parity bit number 2. Number 2 checks for first information, checks for first information, third and fourth. It skips the second one, as you can see on the table. So it goes with the first position, second position, third position, and fourth position. And again, if any one of these 3 are off, the actual parity is off. And we copy this thing one last time, right there. And the third parity checks for number 1, number 2, and the third parity checks for number 2, number 3, and number 4. So let's plug them in. It skips over number 1, we plug in number 2, we plug in number 3, and we plug in number 4. And because in groups 2, 3, and in group where we have 2, 3, and 4, only 3 is on. 3 is only one of those signals is on. 1 is not an even number, therefore we have to have our parity bit on to make it even. And we're gonna just put them like so. We're gonna leave place blank, and instead of this place, we're going to put in bit number 1. I think I just said already that these chips have nothing really important. We can connect this over here, but straight away. But in fact, we shouldn't have connected anything in the first place. We want to be able to invert anything of our choice. We want to be able to invert any bit of our choice. This is where the first rule came in handy, is whenever there's an even amount, we turn it off. We turn it off. If there's an odd amount, we turn it on. This is where the first rule came in handy. This is where the second rule will come in as well handy. We're gonna have 7 positions, 7 switches, because there's 7 bits, and we want to turn any of them off. Okay, 3, and we can copy the XOR gate, just like so. We can copy it there, plug that guy, and we copy it once more and put it in there. I think, yeah. Come on, put it in there. There we go. And for simplicity, okay. So what are we going to do now? Well, now we are just going to take it order by order. So this switch, the first switch, will turn on and off this parity microchip. And this parity microchip is related to the fourth XOR gate, so we're gonna connect the XOR gate right here. And if the switch is on, there's no inversion, but if we turn it on, the signal gets inverted, and this is the wrong thing. So the second one gets connected over here, and right there. The next one is supposed to be a bit, and this is our first bit, so we connect the switch number 1 into there, and from there we connect it into there. And let's actually turn off all of these switches for now. Once all of these switches are off, the signal here should be corresponding to the switches over there. And if it's not, you've made a mistake. So bit number 3, parity bit number 3 is connected into position number 4. Number 2 is connected to position number 5, which is then here. This is connected into position number 6. And the last one is connected into position number 7. And what we are left with is we are supposed to have a 1, 0, 1, 0. We have a 1, 0. We don't count the parity bit, okay? We don't count it. 1 and a 0. Okay, so let's say that there is a mistake somewhere. Let's say it's a parity bit number 3, which is in the 4th position. So let's just invert that, okay? Well, we can now detect in binary which position it is. And to do so, we do basically the same thing what we have done here. We get an XOR gate, we get 2 XOR gates. Now we actually get 3 XOR gates per for every parity bit. Because we are using 3 parity bits, we will need to use 3 XOR gates. We will need to use 9 XOR gates. What do we do now? Okay. We connect the. I think so. Yeah, I think we connect this. We connect the first bit, which is the parity bit, into bit number 1. So we do the same thing as we have done with the table. We connect number 1. We connect the parity. We connect the actual parity as well. We connect the parity, we connect bit number 1, bit number 2, bit number 4. This is the actual parity connected. This is bit number 1 connected. This is going to be bit number 2 connected. And I think so? No, this is not. We're going to connect bit number 2 here, yeah. And I'm going to connect the bit number 4 into there. So now, let's say that there was for example, a mistake not here, but in the first section. This XOR gate is on, saying that, oh, there has been an error. An error. If you switch, for example, this guy will do nothing, because, and this guy is going to do nothing, and that's actually brilliant. I'm gonna explain why in a second. This will turn on, and it should turn on. Position number 3 should be on. This guy should be off. It's off. This guy should be on. This guy should be off. and this guy should be on. Brilliant. That's exactly what we want. Every second one, turn this guy on. If both of them are on, unfortunately there's no mistake. But if one of them is on, then there's a mistake. Okay. And if all three of them are on, it will detect that there is it will detect that there is a mistake. If there are 4 mistakes, it will not detect it, because that's a normal Hamming code. An extended Hamming code would actually detect if there were 2 or 4 mistakes. Okay, back to you. So now we get a microchip. We connect the XOR gate to the first microchip. Okay. Now we look at the second parity. Second parity has parity number 2 and bit number 1 on. So parity number 2 is in position 2. Parity number 1 is in bit number 1 is in position 3. It also looks at position number. It also looks at number 3 and number 4. So this would be number 3 right there, connected here, and number 4 connected there. And now we plug that into the second guy. Now the last guy looks at, well, just all of them. This is parity bit number 3 is in position 4. We connected that up there, and we connect everything below it to the last XOR gates. And we'll connect the last XOR gate over here. So now if we flip this, which is 1, 2, 3, 4, 5, 6, it's position number 7. This displays 7 in binary. This is 6 in binary. This is 5 in binary. That's 4. That is 3. That's 2 in binary, and that's 1 in binary. Okay, cool. Now we need a way to fix the actual message. And to fix the actual message, well, let's say, as I said at the start, the parities have nothing to do with the message. They don't interfere. We can just simply not count them. This is what's important to keep, not the parity bits. So let's say that the mistake was made in position number 1. Position number, in bit number 1. Bit number 1 is at position 3. So we use an XOR gate. I'm gonna have to flip these signals, so we're going to get the result of this, and we're going to flip it. Okay. In the other section, we're using AND gate, and we need to have 3 conditions. So, for position number 1, bit number 1, I can't even say position number 1. For bit number 1 to be on, we need the first 2 parts to be on, 1 and 2, but we also need the third part to be off, so we use a NOT gate. We invert the last section, and if we do this and plug that into there, we get we we get the actual fixed result. This has no change, and if it doesn't change, that's a good thing. So what we will do now is we will clone these three objects 3 times, no, 4 times, because there are 4 possibilities that we need. So we're gonna clone this 4 times. One of these possibilities requires all of them to be on, so we don't need an NOT gate on the last guy. Okay, next we need to invert signal 2. So let's plug that into there. Signal 2 involves having the first and the last, but not the center one. So we connect the first into the AND gate. We connect the last into the AND gate. And we connect the second into the NOT gate. Okay. Next is the third one. Third one requires so that the top one is inverted and the last 2 are on. And then we connect this into this chip right there. There's something wrong here. And I think it could be because I connected the same thing twice, so I'll remove this. Ah, no, I see where the mistake is. Okay. I didn't invert the signal, did I? No, I did. It's just I nothing. No. Oh, okay. I see. Okay. I see. This is supposed to be connected to there. There we go. This guy is supposed to be connected there, and then the last guy is supposed to be connected there. There is still a mistake somewhere. Because if there is no mistake... Okay, well this will get fixed later, okay. So, position number 4. Position number 4 requires that all of them are on, so we just connect them, just like so. And but I don't know why this guy isn't working. I think it's because I didn't plug it into there. I think I plugged something else. Yeah, there we go. And I think I plugged in something else there as well. There we go. There we go. Yeah, now I see. Okay. And that's exactly the Hamming code right there for you guys. Made a little small mistake at the end, but this is the basics of it. Now, you can actually do this for an infinite amount of bits. It just will take more time. So, for example, if you wanted to make 1511 Hamming code, the way how you would detect an odd number for more than few bits is you would do this, and then it will connect the last two right there. We connect them to an XOR gate, and there we go. There's an even, there's an odd, there's an even, and no matter which ones you flip, as long as there's an odd number of ons, the signal will always be on. If you say, for example, added an extra one right there, all you will have to do is get rid of this. Actually, no, keep this in there. Plug that into there, and voila. There's an odd number because there's 3 of them on. 3 is an odd number. We can do 15. We can check with 15 numbers if they are odd or even. So let's do this. There we go, that's 15. That's all 15 of them. And how we would check is we would connect 2 at a time. So connect 2 at a time, connect these 2. You would connect the next 2. Connect the next 2. How many more? Okay, the next 2. And the last guy. And it would basically make like some sort of like a pyramid. So next we compare these 2 values. Next we compare these 2 XOR gates together. We compare these 2 XOR gates together, I believe. And they basically go in a pyramid. Then we connect these 2 together. These 2 together. Lastly, we will connect these 2 together and plug that into them. Odd, even, even, odd, even, odd. Oh. Similar enough. Okay, I'm too tired to think about it. Okay. Thank you so much for watching. See you dudes in the next episode, and where I will do maybe a bigger Hamming code, or maybe I will do something else. Hope you guys enjoyed. See you dudes in the next episode. Peace.